Sorry about the delay, everybody. I had a second camera going today for part of the live stream and had an unexpected problem with it. I think I've got it resolved. All right, so welcome. Nice to have some people here with me for the live stream. I'm grateful as always for that. Hello, Ember Wolf. So I see in chat on Project 2 pictures. I will do that this afternoon. I'll go look and remind myself about that. But yes, thank you for the reminder. But we'll have a peek at Project 2 today, and then I'll be reminded to go post some screen captures from my own implementation later today. Good morning, Magenta. Good morning, Edcast. Happy Monday to you as well. Nice to see you guys. So we're in week 9, which means that now we are past the halfway point, which is a good feeling. Have a fair amount to do today because I didn't do Project 1 demos last week because I was worried about my ability to squeeze all the content in. But I got to do that at some point, so I'm just going to knock that out today, and what happens, happens. Oh, good question. So Edcast asked, what classes am I teaching in the spring? So I'm not. I'm done. At the end of this semester, I will retire. So you are my last PNA 2 in my life. So you'll be in good hands, though. Pardon me. Sorry, my voice is gunky. Yeah, so for me, I'm done and out at the end of this semester. But you'll be in good hands with the people who are there. Thank you, Ember Wolf, for the congratulations. I appreciate it. Thank you, Magenta. Appreciate it. Yeah, I have been looking forward to the end of this semester. But I'm trying to stay focused because I still got a job to do, and I need to leave you guys in the best position I can leave you in. So yeah, anyway, sorry about that. No classes for me in the spring. So let me do the demos real quick. Uh-oh. Okay, here we go. So really quickly, just so you can see, and I'm just going to dash through them, what some of your classmates did. So very pretty output here, by the way. Very, very nice looking output. So let me just buy some stuff. Check out. So let's do 1191. So anyway, that's a very nice looking one. Has a pretty receipt. Shows the change that's due. They use floats, which was the requirements didn't limit you on the way that you handled money. So that's a very nice looking one. Oh, sorry, there's some chats going on. Oh, thank you, Isnam, for the congrats. Yeah, Ember Wolf. Well, like as not, Ember Wolf, you're gonna earn your A, so you won't need any of my help. I would bet anything to walk away with an A in the class. Okay, so another couple of, just again, so you can see what other people did with their projects. So most people, I think, probably did what I would do, which is kind of just go with a straightforward thing. Although I like these ones where you can choose how much you want to purchase. This one has the dynamic display in terms of just saying 0 in stock, saying sold out, while maintaining alignment, which is very cool. Not by again, 1941. And yes to a receipt. So that was a very nice implementation. Now I gotta wait for the REPLs to reset apparently. So this person added extra items, which is quite cool. So let me just buy some stuff. I'll go ahead and buy out the candy, and then I'll buy a couple of others, and then I will check out. So nice receipt on that one. Let's just pay 20 bucks. So anyway, very nice looking receipt on that one. Good job. And then a few more, and then I'm going quick just so you can kind of see on the screen what some of your classmates did. So here's another one. This person put a little banner at the top, which is a nice choice. Let's buy some water. Let's see if it's out of stock. It is, okay. And then I will pay $5 this time. View the receipt, and this receipt was also nicely done with some nice formatting work. So always kind of appreciate when I see the extra effort that people put into adding the extra touches, and that receipt being so nicely formatted is just kind of nice extra touch. So good job on that one. 2 more. This one was nice that it already started with the sold out item, so that was a good idea. This one also uses screen clearing, which is quite nice. So very nice touches on this one. I'll go ahead and check out. I'll pay $15 for this one. I think that one may not have computed the change, but anyway, overall the display on that one was quite nice looking. And then one last one. Just again, to stop and celebrate a little bit the good work that people put into various aspects of their code. So this one has you pay on the spot, which is perfectly fine. What did I buy? Oh, I bought a water. So anyway, you can kind of see what's going on with a few of those. So this one's issuing a receipt with each item purchased, and that was in line with the requirements as well. So anyway, there's some quick Project 1 demos, just so you can see what some of your classmates did with it. Okay, so there's Project 1 demos out of the way. Hold on, I'm going to clear my throat, and I need to do a good one, so I'm going to turn off the volume for a sec. All right, hopefully that's all the more that I need. Maybe water would help. Okay, we are in week 9, and we are finally hitting better and better stuff all the time. So we're getting into the meat of the class. Talking about pointers this week and a variety of other things that we will experiment with to go alongside our, for some of us, our first experience directly with pointers and pointer syntax in C++. Pointers are hard. The syntax is hard. It takes a while to sort of develop the muscle memory for pointers, so just be patient. I've probably said that many times to you about being patient with new concepts and new syntax. Pointers have a lot of syntax. C++ generally has a complex syntax, so we'll make things work. We'll be patient in terms of a sense that we fully understand a thing. That will come with practice. But this is one of the stars of this class, really, is pointers and the associated concepts that go along with pointers. And they are really the reason that a lot of us use C++ in this class, is so that we have access to these features of C++ that you can then learn memory management techniques, which not all languages require that you learn how to do. So those of you who took Programming Algorithms 1 at Butte College in the Go language never did memory management, because Go handles the memory management task for you. C++ exposes to the programmer the ability to manually manage memory in your applications. It's intimidating at first, but it's kind of cool. And we will need to use these memory management techniques for the rest of the semester to implement the data structures and associated algorithms that we're going to use. So pointers are a big deal. Let me pop up the second. No, I'll do it from the reminders page is what I'll do. So let's walk through the module, and then I'll switch over to a REPL. I don't know why I closed REPL it, because I'm going to need it back. But anyway, we'll walk through the module. I'll take a peek at the second project and then leave that as a reminder to myself to get the screen captures up for you. Lab 9, bunch of new syntax associated with pointers, new operations associated with managing memory, a new concept, garbage collection, and then another new concept, which is exceptions. And I want you to be exposed to exceptions at the moment that we start doing dynamic memory stuff, because exceptions are a useful tool for capturing memory management problems. So that's why all of that kind of in one place. A bunch of stuff going on, but we will all kind of use it in a single context. So hopefully that will help you make sense of what's going on this week. So a fair amount of readings to pick from. You probably have started to decide upon which resources you like. You may not like any of my resources. You may have found something somewhere else, but a bunch of options for reading about the various techniques that we're exploring this week. The lab, I will come back to that in a moment. So the Piazza discussion, hopefully slightly more interesting this week, even though I know it's kind of asking a lot of people to kind of trot over the same ground as the people who got to the discussion before you did. But the more different ways we have of explaining these concepts and the more different people we have using their own words to explain them, I think the better. So I read through everybody's comments, and I hope at least you take the time to scan and kind of see what your classmates are coming up with in terms of explaining these things. So indirectly, we will talk about garbage collection. C++ is not a garbage collected language. The Go language is, and many other languages are garbage collected, but there are also many languages that are not. So in your computer science training, it is useful to be exposed to garbage collected languages like Go and non-garbage collected languages like C++. And also you'll sound cool if you can talk about that concept with other programmers, in my opinion. All right, so lab as always, discussion as always. Let's go look at the project. Yeah, okay. Oops. Yeah, so I will do some screen caps off my implementation of this project. The reason I did this, by the way, is because I changed the project. It's sometimes I will try to reuse some old projects that I thought worked well, and sometimes I want to make changes to a project. So this project I have not used it exactly like this before. So I had to make a new implementation, and I haven't gotten around to the screen caps, but I'll do that this afternoon. So the second project is due. When's it due? On October 30th. So a little less than 2 weeks from now. But what it is at least what is likely to happen. Let's look at the requirements. Yeah, it doesn't even tell you how to structure the data, but I will tell you that your life will be a lot easier if you create a struct or a class to model the data in this project. You will need the ability to open and read a file. You will need the ability to parse the contents of the file and populate instances of a struct with that. You will need the ability to take instances of a struct and connect them to some. Oh no, you are required to use a struct or a class, and you're required to use a vector. So you'll take your populated instance of struct or class and append it to a vector, and then you will create an interactive program that allows your user to select different views of the data. And the views of the data will all be related to different ways of sorting the data. So we'll go back to that same sorting techniques that we did in lab last week. So at this point, you know how to do the struct, you know how to do the file reading and parsing, you know how to do the sorting, populating of vectors and sorting of vectors. So the last things that you'll need to implement that you haven't done, at least not directly in this class before, are an interactive menued program. And you did do one of those for project one, but the menu will offer these options on the project. and also these options. So it's going to be a long menu with lots of options, or if you want to, you can have sort of a meta menu with sub-menus. I doubt that's what I'm going to do in my implementation, but anyway. Yeah, so a menuing system, you did that on the first project. And then the one thing that I guess we probably haven't done directly is we haven't looped through a vector to capture a specific field out of each element of the vector to compute an average. So that's kind of the thing that no lab will have exposed you to just yet. Okay, question in chat. So, okay. So the file doesn't have any comment lines in it. Oh, but we need to see it raw. Oh, that first line should have a pound at the top of it. That's a lot of stuff. I bet I took the pound off because of this thing. Okay, so that's a good question. There's a question in chat about what do we... So every line will have the same fields. So every line in the data file should have exactly the same fields. So that shouldn't be a worry that you would encounter lines. Yeah, so every line should have every same field in the same order populated. So you won't have any not applicable fields. In terms of fields that you don't need, so that may be what you're asking, Emberwolf. Fields that you don't need for the second project, you just sort of read past them and throw them out is what I would do. There's different ways to do that, but probably I would just sort of have a throwaway string. And as I am parsing the fields, I'll just kind of parse a field, even though I know I don't need it for the model. I'll just parse it, do nothing with it, and then parse the next one. And keep doing that until I get to the next field that I need for the model, and then populate the model with that field. So hopefully that makes sense. The other question is about comment lines. So can I do something with that today? Maybe. I'll do a quick example today just to show you. But what you should do with lines that begin with a hash symbol is ignore the entire line. I'll show you a quick piece of code today. Let me put it on the agenda. Okay, so we'll deal with that with an example. So it's a good question. What do I do with fields in a file that I don't care about? And then also, what do I do with fields in a file that there are lines of a file that are potentially comments? So yeah, you're right, Emberwolf. There are a lot of fields. So this is a real data set, a real world data set. But for our project, we're going to ignore some of the fields. So we'll just, well, we need to parse them to get past them, but we'll just ignore them. We won't. At least I wouldn't. You're free to create a struct to represent every field, and then your application won't use it. But for me, so as an example in this data set, if I don't need the sodium field, I won't have a sodium field in my struct. I'll just parse this piece as I am processing each line of the file and then do nothing with it. I'll cook up a quick example for that though today. Okay, so there's that. Let me get the lab queued up. All right, so we're doing pointers. I'm going to show you some of the syntax, and I'm going to switch views and draw a couple of pictures. So pointers are not easy. There's a lot of new syntax, and they make people very uncomfortable at first. So that's to be expected, and it's not anything to worry about. You are going to fight the compiler over pointers some. At least I did when I was learning pointers. So you just get used to it. So let's do the most basic thing. So the weird thing about pointers is that they aren't the thing, they are a reference or a pointer to the thing. So if you can imagine two people standing next to each other, and one of those people points to the, hi Tony, nice to see you. I see Tony in chat. So if you have two people, a pointer to one of those people is like one of the people pointing at another person. Almost you can think of like a disembodied arm pointing at a person. So I will show you the code real quick for just a basic pointer. So let's make a string first. Call it the message, and I will just say hello. So not a pointer. A string. Okay, so now let's do the pointer part. But one of the things that it's easy to get confused about is the stuff that you already know. So that's just a string on line 4. It's the same string as you long since know strings to be. Nothing changes about that. And I'm going to be very explicit in my naming for now. So we'll just start with this most basic kind of syntax. So message is simply a string, like you already know them. Pointer to message, which you notice the new syntax is a pointer to a string. So it is not a string, it is a pointer to a string. It's like a disembodied finger pointing at some string. And in the case of pointer to message, this null pointer value, which is a value in C++, tells you that this pointer to a string doesn't point to anything right now. It points to nothing. Let's see what happens if we print it out. So the way C++ will render that null pointer is 0. But we'll use nullptr, which is a C++ value or representation of a pointer pointing to nothing. And you can kind of just imagine me kind of pointing in the air. This is a null pointer. Can you see my pointing in there? Yeah, so get it in there. Null pointer. It's not pointing at anything. It's just pointing up in the air. That's kind of what a null pointer means, is it's pointing at nothing. Okay, so let's make it point at something. And immediately we get new syntax. So let's take pointer to message and point it at message. So another new piece of syntax. Is this ampersand, which I know we already used the ampersand in different contexts. In function parameters, that ampersand means reference, which is not unrelated to pointers. but we conceptually describe these as different things. So a reference parameter is kind of a hard link or a read-write reference back to some original piece of data. In this context, that ampersand represents the address of something. So pointers to things are their addresses. And when we say address, what we mean is the location of a thing in the computer's RAM, in the computer's memory. So now pointer to message, we have, I got to see it so if you can see my hands. Yeah. So we have message, which is an actual string. And then where does this come in? Yeah. And then we have pointer to message, which was pointing to nothing. Now points to the message. I'm going to draw pictures of this, which is why I was 5 minutes late today, is because I needed my overhead camera set up and it was not cooperating with me. So now pointer to message points to message. And what is the big deal about that? Well, it turns out that if we have the message and we have a pointer to it, we can use either of those roots to access the message itself. So here's another new piece of syntax. So now we are dereferencing the pointer with this star. And I know it's very off-putting because the star can mean multiplication in one context and the star can mean dereferencing a pointer in another context. And how do I know which is which? How does C++ know which is which? And it's all context. So if the star is sitting next to something that's declared to be a pointer, which pointer to message was declared to be a pointer, then the star sitting on the left-hand side of it means dereference it. And what we mean by dereferencing is I don't want the pointer, I want the thing being pointed at. So if pointer to message points at message and I dereference it, I get the message. So I'm just going to print that out without a label on it. And let's see what it looks like. So there's hello, which is the message, which we are accessing by dereferencing the pointer. Kind of weird, huh? And anything about the message, let me put another blank line in here. Anything about the message that we want to do, if we have a pointer to the message, we can use the pointer to operate on or with the message itself. So for example, we can say, let's put a label here. Message via pointer. And let me fix these comments. Actually, I'll just put them above it now. Just cleaning up. I think I can fit it all in one line on this screen. Yeah. Okay. So there's the message via the pointer. We can get the size of the message via the pointer. This one's going to look even weirder at first. So we dereference the pointer. And then we want to do this, dot size. The problem with this code here is kind of an order of operations problem. So what C++ is going to want to do, well, let's just run it. We'll get an error, and let's see what the error looks like. Okay, so notice right here, we've got something going on. So C++ doesn't know how to work with this situation natively. It doesn't know in what order to dereference the pointer and in what order to try to get the size. So what C++ is actually trying to do is it's trying to ask what's the size of the pointer, but that makes no sense because size is about strings, not about pointers to strings. So the way you fix this is you force C++ to get to the thing first. Let me move this down. So we will force the correct order of operations. So get the message first and then get the size of the message. All right, so it's a size 5, which is what we knew. We could do other things with this, by the way. So we can do, we can get the first character. So we can do pointer to message, and we already know that we ought to be careful about this. We can get it this way with the square brackets, or I'm just going to quickly grab that. Or the .at. And notice I am forcing C++ to get to the message before it tries to get to the character in the message. This stuff is very intimidating at first. It's a lot of new syntax, and it's complicated syntax. So it takes some getting used to. It takes a lot of practice, and we will get a lot of pointer practice from here to the end of the semester. And you're going to have extended compiler battles because of these pointers. Just I know that because I had them. I still have them sometimes. We all experience this fighting with the compiler to get the pointer syntax correct. All right, so Emberwolf asks, why would I want to point at a thing as opposed to just using the original? And we'll build up to that, Emberwolf, but our application of pointers are going to be that we can actually use them to allocate memory after the program has already begun to run. And that gives us the ability to do all kinds of interesting things. So the pointers, we're starting with the basic syntax of the pointers. And then when we get to why do we even need them in the first place, then we'll see that they give this pointer syntax is kind of the entry to manually managing our memory for our applications. So to do manual memory management, we need to know how to use pointer syntax. And we'll do all of those things today, even though I'm already kind of sweating the clock. Okay, so just to show you that, yeah, so if you have something that points at something else and you dereference it, then you can use the dereference pointer just as if it were the thing that's being pointed to. There is a simpler syntax. Well, at least I would call it simpler. So there's an arrow syntax for some of these things. So for example, the size of the message. We can use this syntax instead, which is what most of us will use because the syntax looks like pointery stuff. At least to me, this looks a lot more like, oh, I'm using a pointer to get at a thing. So this is what I would call a simpler syntax. We can use it to get the first character. You can't use this arrow syntax. I don't think. Let's try it. I've never done it before, actually. I don't know why. I guess because it doesn't make... I'm pretty sure you probably can't do this, but let's try. My guess is that's going to throw a compiler error. Yeah, so it cannot handle that. It has to be just a regular function call. Is what I thought. That was not going to work using arrow syntax. So if you want to use the square brackets, then you have to go the order of operations way of using your pointer to get at data. Okay, so there is some basic pointer syntax. I'm going to comment all of that and leave it at the bottom and make something new. Okay, so the question was raised, and I said I would, maybe I should put these, what order did I put them in? Okay, I did do new and delete next. Okay, so why do we need pointers? Why do we use pointers? Most of the time, and in fact for us, pretty much all the time, the reason why we want pointers and we will use pointers is because they are the gateway to managing the memory of your applications dynamically. And what do I mean by that? So we can do this kind of thing instead. So we can make a program. I'm going to use, at least try to remember, to put a P in front of my pointer variable names during this live stream to help us keep track of which ones are pointers. Okay, so when we have a pointer like P message that can only be used to point at strings, we can't point it at other things. We can only use it to point at strings. But we can take this pointer and we can actually use it to allocate memory dynamically. And I'm going to draw a picture here in a moment with my overhead camera to try to explain this this idea of dynamic memory. Okay, so this operator new is basically a request to the operating system to allocate more memory than the program had initially when it started running. The reason why we want to be able to do this is because it allows us to create software that is dynamic in its nature. One example would be like a music player piece of software, like iTunes if you're on Apple, or even in Spotify. When you create a playlist, the developers at Spotify or iTunes have no idea how big your playlist is going to be. Could be one song, could be 1,000 songs. They have no idea how much space to set aside in their program to account for your playlist. So what they do instead is they use dynamic memory to allocate space for your playlist as it grows on the fly. This is the huge advantage of dynamic memory, is that you can allocate more memory as it becomes necessary, as you need it, in those situations, which is most of the time when you could not possibly hope to guess how much memory will we need. If you were a developer at Spotify or on the iTunes application, how big do we make our playlists? Well, I don't know. They could be anywhere from 0 items to thousands of items and everything in between. Well, we should use dynamic memory instead. We'll just write code that as more space is needed, we will allocate it. By the way, vectors do this kind of for you outside of your view. Vectors also dynamically allocate memory as you add new things to them. You just can't see that happening. So now we're seeing what is actually happening. So when I use the keyword new, I am getting dynamically allocated memory, which means that now my program is not limited to my guesses about how much space is going to be needed. I can just allocate memory as the need arises on the fly. And then I can use that memory through the pointer. So notice that I have no string here. I only have a pointer to a string. But if I dereference the pointer, this dynamically allocated string becomes available to me. and those other operations. So what's weird here is that there is no string in the code per se. There's no actual instance of a string that I have coded for. The instance of the string is allocated on the fly once the program starts running. But this string data will not exist until the program's run and this call to new to create this string on the fly happens. Once that has happened, then I can use the pointer and access all of the information about that dynamically allocated string. The downside to dynamic memory, the upside is that you are now free to implement software that does not have to know in advance how much space might be needed for its various storage needs. You use new and allocate memory as the need arises. The downside to all this is that C++ won't clear up that memory for you. That doesn't seem like that's going to be a problem for such a small program like this, and you don't really understand at first why that's a problem. But if you've ever run a piece of software, Firefox is a good browser, I'm not saying that, but there have been editions of Firefox in the past that kind of just seem to chew up huge amounts of system resources. And at least sometimes it's likely that the reason that the Firefox running is chewing up your system's memory is because it's allocating stuff on the fly and then not cleaning up after itself. So this is garbage in terms of using a system resource, which is RAM, that won't be cleaned up automatically. So in C++, if you dynamically allocate something with new, then you have to manually release it with delete. And all you have to do is call delete on the pointer that's pointing at the thing, and the system will know what to do to clean it up. But if you have a new, then you need to do a delete. If you don't, you are consuming memory resources on the computer that you're not giving back to the computer when you are done with it. Someone in chat might know what this is called, by the way. Does anyone know what it's called when we make a mistake of allocating memory and then not releasing it later? Good one, Tony. Yes, it is a memory leak. That is exactly what that is called, and it is wasteful. So the term we use for not doing a delete on new in C++ is a memory leak. And the idea there is that you are consuming the system's memory resources, and if you don't release the memory you are consuming, then effectively that memory is leaking away from the underlying system and it can't be used elsewhere. So it's a bad thing to do, to have a memory leak. All right, so here's our full program. We dynamically allocate some memory. We use the pointer to print out the dynamically allocated string data, its size, and then we release that memory back to the system so that we don't create a leak. All right, so there are, as expected, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 characters. That's correct. And then we clean it up. Technically, you should always do this as well. So this is another weird thing about pointers in C++. Deleting the thing doesn't mean that your pointer knows it's gone. And let's see what happens. It may or may not do what I want, but let's see what happens if we have freed the memory and then we go back later and try to print it again. It may or may not print. Sometimes it will with garbage. Okay, so fortunately this one crashed. This is going to be the thing that you're going to get to when you get the syntax down. You're going to have to then deal with runtime problems with your pointers. So you will see this a lot this semester. This is a seg fault. And it is going to happen to us 99% of the time when we try to use a pointer that no longer points to something valid. So I'm trying to dereference p message, but I just freed that memory back to the operating system, and that caused a seg fault. So one thing that we will get in the habit of doing is nulling the pointer after we've freed the memory. So we want to be careful to do this extra step, because then we can write logic in our code to check ourselves to make sure we're not trying to use null pointers. So the value of this null pointer setting is that we can use it to check and make sure we're not trying to do operations on null pointers. I'll try to introduce mistakes like this on purpose so you can sort of help me debug today. All right, so we use new to allocate on the fly, and then we dereference the pointer to get at the dynamically allocated stuff. When we are done with the dynamically allocated thing, we delete it, we null the pointer, and then we are careful as often as possible before we even use a pointer to check to make sure it's not null. And in fact, it would have been a good idea and I'll use the short form. So you can just check a pointer like this, just if p message, although I'll probably use null pointer so you get used to seeing it. It's good practice when you have pointers and you're about to dereference them to check to make sure they're not null. Yeah, it's a lot of information, isn't it? Before I go to draw some pictures, the last thing I'll tell you in terms of these null checks, this new is not a guarantee. It's a request. So when I use the new operation, I'm basically requesting that the operating system provide my application with more memory resources. And it's possible the operating system doesn't have any resources to share at the moment. So new can fail. And when it fails, the pointer remains null. So whenever you do a new, it's probably not a bad idea to check for null, because the new, in theory, could have failed, although that's rare in our class that we're going to run out of memory. But the system can run out of memory, and a new can fail, which yields a null pointer. So now we're getting into like really meaty computer science kind of stuff. Okay. Now let me go talk about new and delete from the picture drawing perspective. I like to use pen and paper for this, so sorry about that if you don't like it, but I am much more fluid this way than I am with a drawing tablet, which I've tried and I just didn't like it. Okay, so this is trying to give you a different look of how pointers work and how dynamic memory works. Let's see, do I want that flipped? Yeah, I do want it flipped. Let me flip this. Can I flip it? There we go. Better. Okay. So, except for I'm going to have to... No, it'll work. It'll work just fine. Let's see if my writing looks funny from where you're sitting. Yeah, it's backwards. Oh, I need to flip it horizontally too. Oh, I know what I'll do. I'll just move all that around and then not flip things. Okay, yeah, that's better. Okay, so when we're talking about dynamic memory, it is helpful to have the concept of stack memory versus the heap or free store memory in your head. The heap or free store memory is on-the-fly memory, meaning that this is where conceptually your new requests get memory from. Stack memory conceptually is compile time memory. And then the other things to remember are that the stack is cleaned up for you and the heap you clean up. All right, so a lot of words. So this is all RAM, and the pictures are here just to illustrate a concept. So we have the system's RAM, but as a programmer, we kind of have two areas of RAM that we work with. The RAM itself is managed by the operating system. So when we launch a program, when you click run, for example, in Replit, the system sets aside a certain amount of memory for your software based on what could be determined at compile time. And then the operating system itself has a whole bunch of free store memory that you can request on the fly as your program is running. The upside to the kind of the known or compile time memory is that it is cleaned up by the system for you. So if the compiler can see what you have declared, then the compiler can kind of help take care of the problem of cleaning those things up for you. If you are using the keyword new, then those things are not going to be cleaned up for you. You're going to have to clean those up for yourself. And by clean up, I mean release back to the system. All right, so there is stack and heap. I'm going to go ahead and fill in some more stuff on this. In fact, no, I'll just start another picture of it. Okay, so let me draw a new picture of stack and heap. This is all RAM. These pictures are here just to kind of get it in our head that there's some memory that's kind of known to the system at compile time based on what I've declared. And there's other memory that's not known at compile time because I use the keyword new to allocate it on the fly. So let's draw ourselves a stack and a heap. Oops. And then write some software and see what the effect on the stack and the heap will be. So I'm going to do a little bit of back and forthing here, and hopefully this is not too off-putting. So let's make a new program. And by that I mean just comment this stuff out and make a new main. Just a couple of examples. So this is a declared, a static, we would call it. A static integer and a static string. What do those look like in terms of the system's memory? So they both go on the stack. Did I put a value in there? Conceptually, at least. Both of those things I've declared go on the stack. The nice thing about the stack, the things that I've declared as static, just regular old variables and objects, is that the memory will be provided when the program is launched, and then the memory will be cleaned up when the program shuts down. Same is true for local variables and functions, by the way. When the function executes, any variables declared inside of it will be allocated on the stack and then released from the stack when the function returns. So we like static variables a lot because there are a lot less problems associated with them. All right, so now let's go do something else in the code. Let's point at the, for starters, let's point at the integer. So we need an integer pointer to point at integers, and I will make it be null pointer to start. Okay, so what does that look like on the stack? Looks like this. Somewhere in here anyway, we have pint, which is kind of, do I have a pencil? I do have a pencil. Kind of points off into nothing. So here's pint, which I've drawn a dot there to remind myself that it's a pointer. But notice that the pint, the pointer thing, is actually on the stack. And presently, it kind of just points off into space at nothing, which I call null pointer. So there's my stack when this program runs. And let's use pinteger in two different ways. So the first thing we'll do with pinteger is point it at something else in the stack. So I will point pint up at the integer x that is on the stack. So what does that look like if I draw a picture of it? Hopefully my eraser works enough. So it looks like this. Basically, this pointer points to this integer. It's kind of like an address book if you want to think about it that way. Pointers are simply addresses, and if you go get the address, you can get to the thing that it's the address of. But I like to think in terms of pointing at things because it's just easier for me to understand. So the code I've written, pint equals &x, means point pint at the same address that x lives in memory. So that's what we have here. Now, so far I've not used the keyword new. All I did was point from a pointer on the stack to an integer on the stack. But now we're going to use, so there's nothing to delete here because I didn't use new anywhere. Now let's instead take pint and allocate an integer's worth of space for it on the system. So what does that look like? So I have taken pint and instead of pointing it at x now, I have actually requested a new amount of requested memory space on the conceptual heap, big enough for an integer, and pint is now referring to that location. So there's pint referring to that location. And now let's write the code to, oops, I forgot to switch this over. Let's write the code to populate that memory. So I'm going to dereference the pointer, and I'm going to deposit a value there. So pint equals, dereference pint equals 99. So what does that look like in my picture? So I am dereferencing pint, meaning I'm going to the memory location that it refers to, and I'm going to deposit the value 99 there. So that's what I just did in code. Okay, so now I'm going to, heads up, make a mistake. So before I draw the picture of it, does anyone detect a mistake here? Okay, let me... Oh, wait, I didn't show you the code. Sorry. I think I wasn't showing you the code, so you didn't know what I did. I added lines 15 and 16. So now maybe that helps you detect the error. So Isnam asks, is 99 on the stack? It is not. 99 is on the heap. Good one, Isnam. So now that I showed you the code, sorry about that. This is a memory leak. So if we draw the picture, we can see the memory leak happen. So what I did is I used this pointer. I allocated another integer's worth of memory on the heap and deposited the value 33 in it. But that bit of memory on the heap that had 99 in it is still there. And as far as the operating system knows, I still want it. That's a memory leak. I'm using this memory even though I actually have no way to get to it anymore. That's the other thing, by the way. There's no way to get back. Once I take this pointer and point it somewhere else, I can't get back. So how do we fix the memory leak in this code? Does anyone know? Nice one, Isnam. On top of it, for sure. So if I am done with this first integer, then I need to release the memory associated with it. At a minimum, I need to delete that memory, which releases that piece of memory back to the system. And it's not a bad habit to be in, even though I may learn that I don't always have to do this. But it's not a bad idea to delete it and null it before moving on. So before I go make any more dynamic memory allocations, I want to, hopefully I changed, yeah, I did. I want to delete. So the delete call will free this. Temporarily, it's going to make this pointer point sort of up at nothing, and then it's going to turn around. So the delete call is crucial because that's how we get that cell of integer memory that was holding 99 released back to the system and eliminate memory leaks. So if you're drawing pictures like this and you find memory cells that have nothing referring to them, those are memory leaks. Okay, so but the important thing to note here is that pint itself is on the stack because I declared it in my code. But everything that I did new is on the heap. So let's finish this one. Let's delete the second one that I did and and null it out. Before I let the program sort of bottom out. Okay, so that's new and delete. Now we have the rest of the semester to do pointers, so we're going to do lots and lots and lots and lots and lots of pointers. Because they're really the for the data structures we're going to explore in greatest depth, we need pointers to pull them off. We can't create dynamic data structures without pointers and new and delete in the mix. So you'll see on the agenda, am I still, okay, I switched back to something that looks nicer. You'll see on the agenda that I say new and delete versus garbage collection. So the fact that we have to do a delete with our new in C++, that if we allocate memory, we have to deallocate it manually. That means that is why we say that C++ is not garbage collected. There are systems like Java as an example, and the Go language as well. Java and Go will let you allocate memory on the fly, but they keep track of your dynamically allocated memory and release that memory for you when you're no longer using it. That is what garbage collection means. So garbage collection means that dynamically allocated memory is released back to the system automatically when the program is no longer using it. You might ask, why don't we just do that in every programming language? It's expensive in terms of processor and memory resources to have a garbage collector. So the upside of garbage collection is that you don't get memory leaks. That's a good thing. The downside of garbage collection in languages like Java and Go is that they have to run a whole subsystem that keeps track of all your dynamic memory for you and frees your dynamic memory for you. So there's a performance cost to garbage collection. So the upside to manual memory management, like we do in C++, is that we don't have the overhead of a garbage collector. We get the efficiencies of manual memory management. The downside to manual memory management in C++ is that it leaves us open to the possibilities of memory leaks, which you will create lots of them in your life if you work in C or C++ or a not garbage collected language. So that's the downside, is that it means that we programmers make more mistakes when we are left to manage these things for ourselves. And that's just a fact of life. So anyway, there's goods and bads to both. It's nice that we have choices. So if we don't care about the overhead of a garbage collector, then that might make sense. If we care about the efficiency of not having garbage collection done for us, then maybe C++ makes sense. Okay. So what else do I have in there? I have exception handling, passing pointers by reference, and then that file processing thing. So to accommodate the file processing thing, I'm going to load up the lab code and give you some tips directly inside of it, I think. Yeah, I think I'll do that. So let me make a this is lab 9. So let me go quickly grab the lab code. And I guess to compile anything, I'm going to need a doc test. So I don't know why I didn't just grab that. Okay, so the rest of the topics in the context of this week's lab. And I'm going to kind of go light on one of them and just sort of give you the introduction and give you enough that you know how to use it. But I am going to give you a fair amount of examples in here to help you out. In fact, a lot of examples, because this is hard stuff. So hopefully, though, you'll take the time to kind of go back and revisit all these things. Think about what it is that you're doing. So let's just go through it. I think that's the best way. The best thing I can do for you is just to go through it. So this first function, there's going to be new stuff going on, but basically allocate memory for a string for these contents. Okay, so let's go to c++.com and see how do we make a string of another string. Make sure you can see what I see. You do. Okay. So can we make a string of another string? Well, we want to look in constructors for this. And it turns out that we can. So notice this second constructor builds one string, and you'll see the word copy next to it if you get up close to it. Builds one string as a copy of another string. All right, so that's what we want. So we simply call the string constructor and pass it another string, and it will build a copy of the first. Okay, so but the other trick here is that we need to return a dynamically allocated string or a pointer to a dynamically allocated string. So what would this look like? We'd do this, I think. So we'd say string star. So we need a pointer, p string, and then we're going to dynamically allocate it. So I'm going to use new to pull that off. And then we use the desired string constructor, which is string constructed as a copy of another string. So we take these contents, we construct a string dynamically, and then we have this pointer pointing at the dynamically allocated string, and then we are supposed to return a pointer. So this is kind of weird that we're allocating on the heap and then returning a pointer. But when the caller of this function receives the pointer is still referring to the dynamically allocated memory, so all is good. So that's that whole function. Allocate the string of those contents dynamically. We need a pointer to do that. And then we return the pointer that we used to do that. And now whoever calls this function will receive that pointer, which lets them also access the dynamically allocated memory. Potential memory leak here, by the way. This is one of the complaints about C++. This function is allocating a string and losing entire control over that dynamically allocated string. So whoever calls this function better make sure that they know that it was dynamically allocated, because they need to release that memory when they're done with it. This is one of those places, though, where mistakes can happen. I have one function allocating memory for a string. I have another function that calls for a dynamically allocated string, and it's the caller that has to remember that it was dynamically allocated and needs to be freed later. So this is a good chance that mistakes can be made with less than very careful programmers. When you have the allocation happen in one function, then you're just kind of crossing your fingers that the deallocation happens when it needs to happen. Okay. So now we get a new concept on this one. This no except. We're going to get more into this because we're going to use it for the rest of the semester. But this notation on a function means that it is an error point. And when you see no except false, what that means is that exceptions can happen here. You should read about exceptions from the readings this week. But an exception is kind of an extraordinary circumstance in programming, which unfortunately is a common but extraordinary circumstance. So we use exceptions when we don't have some more convenient mechanism for signaling a problem to other parts of our software. So this is a void returning function. it's accepting, we'll talk about this ampersand here in a moment. It's accepting a pointer to a string by reference. And it is, it's a goofy way of doing it, but it's saying that I might cause an exception to happen. And in this case, maybe I'll drum up a sample of this so you can see it happen. That really means that seg faults can happen here. And we can head seg faults off if we code for them. So another way of saying no except false is, this is a function where the program can totally crash. It can totally crash because if this pointer is null and we try to free the memory at the other end of a null pointer, we're trying to free something that doesn't exist, and we will cause the system to crash. So that's what this is really saying is, heads up, this function could cause a crash. But we can actually handle crashes from in the code and stop them before they actually shut the whole system down. I'm about to drum up an example of that. In fact, let's go do that now. So let's look at an example of an exception. That's not what I want. Stop it. I wanted the other one, week 9. Okay, so let's just do one of these real quick. So we'll go ahead and do our same Now I finally figured out what was wrong. Crashes can happen here. So the basics of these two functions are allocating a dynamic string and deallocating a dynamic string. That's all that's going on here. This exception stuff looks a little bit goofy, but it's for very practical reasons. So let's just see how this works in practice. So let's make a string pointer in here. And just for fun, let's try to clear it. So let's just go straight to what happens if I try to delete on a null pointer. It should have crashed, which I'm unhappy that it didn't do. Is it really not going to crash for me? Oh well. It ought to crash. I don't know why it's not crashing. I don't know. We'll try it in some other way. This is a good thing. But anyway, technically, this can cause a crash. Let's see if I can make it crash. Let's see if I can make it crash with a message. Okay, good. At least I can make it crash with this little debugging message, freeing. All right, so this is the thing that I am worried about here in this function. Technically, deleting a null pointer, I think, can still possibly sometimes lead to this. But hopefully everyone understands the basics here is that I never allocated anything, and then I'm trying to free it. The process of freeing it, I tell you what string you're getting rid of. which in this case, because I never actually made a string, caused the system to crash. So that's why this no except false is here, because it allows us to handle the code, the situation where we have kind of an extraordinary circumstance. What's extraordinary here is that they want us to release the memory or deallocate the memory that was never allocated in the first place anyway. So how do we do that? Well, in the function where the crash could be caused, this no except false means I'm going to perform some logic here that will signal if this extraordinary circumstance happens. Now let me go steal some of the code out of this one real quick. That's all fine. Okay, so if I am writing a function that might cause this extraordinary circumstance to happen, then it is good programmer style of me to let other people know that that could happen here. So this no except false means that bad things can happen here, but I can also code to signal that a bad thing happened. And the way I'm going to do that is I'm going to write some logic. So if this p string is not equal to a null pointer, then in theory all is good with the world. That's fine. A not null pointer is fine to print it out. It's fine to delete it. It's fine to null it out. But the other case where it is null is potentially a huge problem. And I can actually handle that in code by saying, hey, you tried to do something naughty. So this no except false, it means I might throw an exception. This is a different kind of logic. It's kind of a higher level kind of thing, or lower level, depending on how you argue it. So here I am telling other programmers, hey, you called clear dynamic string, bad things can happen. But I'm going to be nice enough to let you know that the bad thing happened. So first I check to see if everything's okay, and then I just do what I'm supposed to do. But then I have the otherwise bad thing happened. So throw is the way that you signal to other parts of the program that something potentially terrible was attempted here, and I'm going to head it off. So let's try it and just see what happens if I run the code this way now. So this is good, because the system actually barfs on my throw. The system shut down, and notice that terminate called after throwing an invalid argument. So this is a good thing. You want software to get stuck on bad errors like this. So my function now is better, because if you try to clear a non-existent string, my function is going to throw an exception back at you and potentially crash the system, but that's better than having the system crash in production. Okay, but let's say from this side, I don't want my system to crash. I just want to deal with the problem. In that case, so on the requesting side, I can actually deal with that in a special kind of logic as well. So we can use a try catch. You don't have to do this on your lab, I'll show you. But if we are calling a function that might do a bad thing, and it tells us it might do a bad thing, we actually have the ability with a special construct to deal with the bad thing. So I'm calling clear dynamic string, and when I go read clear dynamic string, it tells me I might throw an exception. And that means that I might crash the system unless you catch the thing that I throw. So it's kind of weird. Takes some getting used to. You don't have to do much with this week, but just so you kind of see all the moving parts. And I'm going to catch that thing. I'll just call it, yeah, exception. So it's a little bit like an if-else. If this thing throws an exception, meaning try to do a thing that throws an exception, and if it does throw an exception, I will catch it. So here I am on the receiving side of the exception, which I am catching now, which means my program no longer crashes, but instead I'm able to sort of pick it up and print information to the screen about it. So, oh no, this happened. And then notice that if I take the exception argument and I use its what function, I get the actual message that was printed that was associated with it, trying to free a null pointer exclamation point. So you don't need all of those moving parts. I just thought our first glance at exceptions so that you know that there's a thrower of an exception and there is a catcher of exceptions in our code. This week, you only have to throw them. You don't have to catch them. I've written the tests to catch them. Okay, so there is sort of the extendo. I'll put this REPL as a link. This is the sample code REPL. The lab code REPL I'm leaving on the screen only, I think, because otherwise I'm just kind of not asking you to do anything for the lab. Okay, so here we are. We have that same function. It's telling us do something when the bad thing happens, and it even tells me what to do. Throw this if the string is null pointer. Okay, so I'll just write it like that. If the string, this pointer right here, is null, something funny, then I'm going to throw exactly what it tells me to throw. And then I can have an else that does the actual cleanup in the case that the bad thing didn't happen. So the bad thing is a null pointer coming in. Not a null pointer is a good thing. What? Delete the string. The string equals null pointer. So there's handling the bad thing. I'm going to be going on for a bit here. I think I'm not going to take a break since we're running up on midday. So apologies, and hopefully you're okay to go on for more. But if I don't take a break, then I'll get done just a little bit sooner. My hope is maybe somewhere in around 15 minutes here. So it's going to take some time to absorb all the stuff that's going on this week. I am showing you a complete implementation of this lab right here on the live stream so that you can get the code right and then spend your time doing the reading and thinking about what the code is doing. And then we will be just beating up on pointers for weeks and weeks and weeks to come. So let's keep going. So this one, so notice that this function is taking a pointer. So we're going to be doing the entire lab by using pointers to get at things. It also has a reference parameter. So populate, that should be alpha, with the number of, what? Oh, wait, I just broke it because, okay, I see. Populate alpha with the alphabetic characters and num with the numeric characters. Can do. I also am expected to throw an exception if the string is a null pointer. Can do. Let me, if I can look better. Still kind of wraps, but I guess I'll live with it. So I always think it's a good idea if I'm doing counters that have been passed by reference, meaning I'm expected to make their values be correct. Let's zero them out. In fact, let's do the quicker way of zeroing things out, which is to let a cascade go from right to left. So 0 to number, and now that number is 0, 0 to alpha, and now they're all zeroed out. Let's check for, in fact, I don't need to do that until the else part. So if the string is null, then I should be throwing an exception, null string pointer, and then everything else is everything else. Okay, so all I have to do here is for each character in, I have to dereference it, it's a pointer in the string. If is alpha, that character, then alpha plus plus. Else if is digit, that character, num plus plus. And that's it. Oh, I'm supposed to return the total number of characters after all of that is done. Goodness gracious. Okay. Return the string dereferenced. Yep. Size. So there's that function. I'm not happy with the no except having wrapped around to the next, but I'll live with it. So most of this code is not new. The exceptions are new, but I'm just going to show you all of them all the way down. So there is count chars, fully implemented. Find word. I'm going to go from memory to enhance speed, but I will point out to you that I am using the standard string class. Let me go back one. The find function. So I'm using the find function of the standard string class. That's not it. This is it. So same thing. If the pointer I get is null, that's a problem. So in that case, I'm just going to throw an exception and be done. If the string is not null, then I can do what I'm being asked to do, which is return true if the word is found in the string. So the word in the string. This is pretty easy to do. So it returns the return value is the position of the first character of the first match. If no matches are found, then the return value is some weird constant called no position. Typically should be -1, but we'll use this as our key. So this is what we're looking for, and I'm just telling you that because I'm about to look for it. So the first thing is size t position. That's what I'm told I get from this function, and then I will the string dereference the find function looking for the word inside of it. If this thing I got back is this weird looking thing, then I did not actually find the word in the string. This is the weird value I get back from the function telling me, nope, it's not there. Otherwise, it was there and I can return true. So trying to find it, the find tells me that I get this weird constant value on a failed find, and everything else would be a successful find. Okay, leave it there for a moment. Replace. So let's go look at the string class again. Replace. Replace a portion of a string. The arguments are important here now. So let's see what the arguments mean. the position of the first character to be replaced. That also happens to be what the find does for us, is gives us the position of a thing. So that's going to be handy. The number of characters to replace. That might be it. Oh, and the string doing the replacing, right? Where did that? Oh, the string being plugged in. Okay. So the position where we want to start replacing things at, the number of characters that we want to replace, and then what's supposed to go in there. Probably. All right, let's try it. This is another no except false, meaning bad things can happen. So let's check for the bad things since we're using pointers all over the place here. The null ones are bad. So that's what I'm told to do right here in the documentation. Else I can do the work. So I have a string and I have a thing that's in that string that I want to replace with something else. So the first thing to do is to go into that string and see if I can find the old thing that I want to get out. Same find. So is the old thing in there? In this example, is the word grapes even in there? I'll know that because of this weird thing. So if I can't even find the old word in there, I'll get this weird constant as a result. In which case, I think I'm supposed to return false. Yeah, return false if the string was not. So if I can't find the old string, well, I can't replace it, which means I can't make any changes to the string. So return false. Otherwise, notice, by the way, it's the same kind of find setup. It's just what we do at the end changes now. So this else part means I could find it. So what I want to do is replace, starting at the position where I found the old string. I want to replace all of the characters, the entire length of the old string, with the new thing. And once I've done that, then I can return true because, yes, in fact, I did alter the string. I don't know if the documentation says it. It's in place, though. Should be in place. Yeah, I think it's in place. We'll find out when I run my unit test and fix it. So there is replace word, as far as I know, fully implemented. All right, let's do the items then. I have enhanced this struct just to show you that you can do this in preparation for future labs. Because structs are very much like classes, structs can have constructors, and sometimes it's convenient to have that ability. So it is a struct, yes, which means the data fields are public, yes. But I've also created a constructor for the convenience of not having to populate each field individually every time I want a new item. Okay, so here we go with the item. Make a dynamic item. Well, to do that, item star p item equals dynamic allocation item, and then I'm going to construct it with this thing that takes a name, price, and quantity in it. So my parameters are new name, new price, new quantity, and now I have a dynamically allocated item populated with those fields using its own constructor, and then I can return that pointer, which is what the function tells me I'm supposed to do. Okay, clear dynamic item. That might throw an exception because null pointers are bad. So it already tells me what to do. If item is null, Then I'm supposed to throw, this time, null item pointer. Otherwise, I'm safe to do what I'm supposed to do, which is free it and null it. So very similar to the string, right? So we can also, if you didn't pick up on that, create dynamic instances of structs and classes, and that's super, super handy. Update item has a no except false on it, meaning I know I'm going to have to do a throw kind of thing somewhere. So if the item is null, I am supposed to throw valid argument null item pointer. Got it. Be careful of the spelling because the tests probably care about that. Otherwise, I can update the item. So I can say item dereference the pointer, name equals new name. That's the parameter. Item dereference price equals a new price. And finally, item quantity equals new quantity. Okay. So again, I'm just going to implement the whole thing with the hopes that you will study the code, and you'll have to type it for yourself, so that gives you a chance to mull it over. And the purpose of this lab is to get accustomed to all of this new syntax, which is why I'm giving you the complete solution, so that you have time to think about the syntax and try to make some sense of the exceptions and the other things that are going on in here without having to pay the price on the lab itself. Okay. Here's another no except false, meaning null pointer bad. But if it's not a null pointer, meaning it's a valid item, then I can calculate its purchase price, which is simply got to dereference it. It's quantity times its price. It's not an accident, by the way, that you've seen this item more or less before. I wanted you to be staring at least some familiar territory here. Okay. Oh, it's a string thing. Wonderful. Well, we've seen this before. It just looks a little bit different. Oh, I forgot. Exceptions can happen, meaning null pointers are bad in our context. Okay, throw. Otherwise, I can keep doing this other stuff that I wanted to do in the first place. Okay. What are we supposed to have? Oh, I have to do the stupid formatting too. That's a pain. Name, comma space, item, dereferencing the pointer all the way across, space, at, space, $, and then I have to do the dumb formatting part. So I'm going to fail this part of the test. So it'll be the one thing I'll ask you to go look up, because I'm pretty sure that I'm going to fail the test because of this right here. And that's it. So again, familiar things and of course unfamiliar things. These checks for null pointer. So the things to be looking at, and I'll go back through one more time real quick before I stop. Oh, that's everybody. That's the whole lab. Let's see which ones I fail. Or it crashes because I made a mistake somewhere. What? Let me see something. that was on line 207. No name at. Oh yeah, because I didn't even inspect my own output. It's because of that $0 right there. So I leave you with one failing unit test because there is a magic formula needed now on line 162. Agreed. So Edcast points out that the wait time for the test, it can be long. Definitely true. The unit testing library is a gigantoid file. So yeah, the build can be slow, and that can be somewhat frustrating to deal with. So, load up on, caffeinated beverages or what, and stand up or sit back when you fire off the test. Yeah, definitely true. On Replit, these things build and can run slow because the unit test is a complex, large piece of software. Yeah, it makes me feel anxious and impatient as well. Okay, so heads up, everybody. Line 162, I left out the magic formula, which causes this one form of the test to fail. So notice here, that was my output, and the whole difference is that I didn't force the two places of decimal output when I printed out item price. So the fix to that is to put that magic formula for forcing two decimal places in there. Okay, so one quick last scan through to see what are we supposed to be paying attention for. The pointer syntax. So here's a function that returns a pointer to a string. And the reason why it does that is because it's using the pointer for its ability to let you dynamically allocate memory. This function accepts a pointer, and I know that there's a reference symbol in there, and we will talk about that next time. So just let the reference part be. We are receiving a pointer to a string by reference. But the only thing that really matters for our purposes is that we realize that this parameter, the string, is a pointer. And because the string is a pointer, it can be null, and that's bad. But it also means that if it's not null, we can do things like delete the memory being pointed at and then null the pointer out, which is a nice service. The count chars function is a function that we've written early in the semester. The only difference really here is the string that we are working with, we're accessing via pointer. So the string, which is a string pointer, which changes the syntax right here. We dereference the string because it's a pointer, and that's the only way to get to the characters inside of it. Okay, find word. So we have a pointer to one, and then we also have a non-pointer one. The non-pointer one is the thing that we are looking for. The pointer one is the thing we are looking in. So the string could be null, so I check it. It has to be dereferenced to do stuff with it. But the word, since it is not a pointer, can just be used like a regular old string. And then we use this find function, which is something you can go look at a little more closely. But this funky constant string npos, it's how the string, the C++ standard string represents a failed find. So a find gives you a position, or it gives you a not position on a fail. So it gives you the actual position, or it gives you no position at all. Kind of weird. Replace word accepts a string. That's the string we're working on. The old word is not a pointer. It's the one we're looking for. The new word is what we want to replace the old word with. So notice these two parameters are not pointers, so they won't be dereferenced. This parameter is a pointer, so it will, and also it can be null. So no, Magenta, I will not be uploading the lab code because then I would just be having people do a copy and paste operation. So the lab code, I've been working on it for almost an hour. So it may have gotten blurry at some point in there, but hopefully it de-blurs enough times to get at the code that I've been writing. Hopefully it hasn't been blurry for a whole hour. But no, I'm not going to upload the lab code because I wrote the entire complete code and talked through it line by line by line. And I do want to compel everybody to study it by entering it for themselves. Hopefully the video that I upload will not be as blurry as what you're seeing on the live stream. Okay, last few, and I can get through here before noon. So we have an item. I added a constructor. Even though it's a struct, we can do functions and constructors in them, so I did, as a convenience for what comes up. So make dynamic item. The parameters are not pointers, so those are all just normal things. We don't have anything to worry about. We are returning a pointer to an item because we want to dynamically allocate it. So we use new, and we use the item constructor that we defined in the struct, or that I defined in the struct. Okay, here's clear dynamic item. Takes a pointer to an item, and I know by reference is weird. Don't worry about that. It's a pointer to an item. Can be null, which is bad, so we deal with that. If it's not null, then we can delete it and null it. Okay, update item takes one pointer parameter, that's the item to be updated, and then 3 non-pointer parameters, which are the new values for the various fields. Pointer, so that could be bad, so we check it. And if the pointer's good, then we can dereference it and store values there. Calculate purchase price is another, take a pointer, check it for null, and throw an exception if we have to. Otherwise, we just do the work that's requested by dereferencing the item. And notice here that the star means multiplication again, because on either side of it are numbers, which is how C++ figures that out. To string was the last thing. So takes a pointer, could throw an exception, so we deal with that. And then we do the old to string stuff that we've done several times now, remembering that since we're working with a pointer, it has to be dereferenced to get at the fields. So that's a lot. And I hope that the video is clear enough to work with. If you encounter sections of the video that are not clear enough to work with, then my hope would be that we can work together as a group in Piazza and just say, like the video was kind of rough here, and this is what I think I got, and then we can kind of share that result, that cleanup through Piazza. So if you're hitting Piazza with lab questions this week, a good rule of thumb would be to try to contain yourself to problems with the single function at a time. And don't forget, the unit test fails 1 because I have left it for you to insert the magic formula, which requires nothing about pointers in it. It's the same magic formula that we have used before. Okay, so thank you a bunch for waiting around so long. I know this is kind of a lot of new, potentially kind of unsettling looking stuff. Pointer syntax, the pointers themselves, the exceptions. So for my money, the place to focus your energies is on the pointers, and just do the exception things when I tell you that you must for now. Unless you want to go digging in on those, then please do. But the pointer stuff is the key. So the pointer syntax and the new and delete, those are the big things. And then the rest of them are bite off as much as you care to bite off and chew on. But we will be repeating these things over and over and over again for many, many weeks. Well, 9 weeks to come. So Canvas Inbox, Piazza, and office hours this week. Other than that, thank you very much for sitting through a long live stream, and if you're watching later, for sitting through a long video. There's a chance I'm going to split this in 2 parts for those of you consuming the video, because I have a size limit when I upload it to the captioning service. So have a great week. I'm going to leave this on the screen with the one thing that will not pass the unit test because I did not implement it, which is this to string on item. The magic formula is needed, and that's kind of where I will stop my comments. So have a great week, everybody. I will get screen captures up. I didn't get a chance to do the what do I do with the comment in a file, so I'll push that forward into my notes for next week, and make a point of getting to that next week. So have a great week, and I will see you, if not in office hours, then on Monday next week, and hopefully I am a little bit more efficient. So take care.